let's get started. Okay, so we will first talk about the homework. There's a crack me 4 in the homework. There is also crack me 4H and 64-bit version. So all 3 versions binary code were generated from the same source code. The only difference are some compiler flags. I will show you later how the flags are different. And also, of course, there's a 64-bit version. By the way, there is a let's check. Don't forget to sign my name there. So this is the source code, and you didn't have access to the source code in the homework. First, there is a global variable, which is just a random string I put there. Then there is a decrypt function to decrypt any string you gave there. Then there is a print secret, which checks 3 arguments on the stack. If all 3 of them match, then it will decrypt and print out. Otherwise, it will just exit here. And the main function here is a variable function. It has a local variable buffer, sacred level 8 bytes. But I've been saying this many times. The 8 bytes, the 8 here doesn't really mean the distance between the beginning of the buffer to the saved EBP or saved RDP is 8 bytes. So the compiler will only guarantee that there are at least 8 bytes. There could be more. The compiler will do a lot of weird things to make things a bit faster. Then you will compare if the argument, command line argument is 2. The command line argument are actually pushed by, the command line argument are actually in the address space of the main program. Maybe next week we will see how it works. Then there is a string copy, which is vulnerable. String copy is vulnerable, and it's going to copy the second command line argument to the buffer, and you can include a lot of the things there to trigger the buffer overflow. So if we look at the easy version, the crack me 4, and this is what we have been discussing in the class, what you are familiar with. The prologue of the program is just a push EBP, move, and subtract something. That's exactly what discussed in the class. So to overflow this one, it's actually easy. You just need to figure out what is the function address of print secret, overwrite the return address on the stack with the function address. Then this 4 byte doesn't matter. We discussed last week why this 4 byte doesn't matter. Then we have those 3 arguments. So this is basically your exploit to exploit crack me 4. So crack me 4H is much more complicated. If you compare the disassembly, you can see it's a little bit longer. So this one is here return. This one looks like the H version looks like much longer. And this is to crack this one, you need to understand the differences, how it works. So we're going to look at this step by step. The first instruction, the same. That's a secret feature we're not using so far, so it doesn't matter. So the second instruction, no effective address. So it's not a standard push EBP, move ESP to ESP at the very beginning, right? It's a little bit weird here. Let's try to figure out why the compiler is doing this. What is the purpose of this? Just the 3-4 instructions. What is the purpose of this? Okay. The first one is no effective address, ESP +4 and ECX. So what this does is ECX will have the value of ESP plus 4. So what is ESP anyway? This is kind of the very first instruction of this function. So ESP actually points to the return address, right? Then we have a ESP plus 4. So we are something a little bit higher than ESP. And this is the main function actually. Remember, this is the main function. Main function has the same prototype. It has ARCC and ARCV, array of ARCV. So ARCC is the command line arguments number. If you include 2, then there are 2. If you do not give it any arguments, just type the program name, then the ARCC will be 1. So after this instruction, the ECX will be ESP plus 4. So actually it points to ARCC there. Then the next instruction, a little bit confusing. We are doing a logic and operation on ESP with this constant fixed number. So this fixed number, you can see that it's obviously 4 bytes, 32 bits, and only the least significant 4 bits, 1F is 4 bits. Only that 4 bits is 0. Everything else is F. So all ones. So if you do a logic and this number with ESP, what will happen? We're changing the ESP, obviously. So the higher 28 bits of ESP will not be changed, right? Because it's 1 and anything will still be that same, so it will not change. But the last 4 bits will be changed to 0. So after this operation, ESP will be smaller. So the purpose of this is similar to what we saw before, for example, similar to there is a subtract something. There is a subtract, right? So this one is a little bit similar. This one is also make ESP smaller. But we don't really know how many bytes we are subtracting from the ESP. It depends on the value of this ESP. But what we're doing is we're making the least significant 4 bits of ESP 0. That's a goal of this instruction. And the reason we're doing this is the compiler wants to have the stack for the main function aligned with 16 bytes. That's why it's doing this. The easier version, this version, we don't have that. At the beginning of ESP just points to return address. The compiler doesn't really care where that is. However, this version, actually, this hardware version is the default version generated by GCC if you do not use any flags. This is the default version. The compiler tries to make it the stack align with 16 bytes. Why it is doing that? Maybe it will be faster. It uses it will be faster if it is aligned. Anyway, that is what we have. Then, so after this one, we know that ESP will be smaller. So ESP will move down a little bit. We don't know how many bytes, but definitely not more than 16 bytes. So after that, we will push ECX minus 4. So what ECX points to here? So ECX minus 4 is here, the return address, right? So you will push whatever is here to the stack. And ESP, previously, ESP points to here. Now we're going to push ECX minus 4, or whatever is that address to the stack. So that address actually stores the return address. So we're going to push the return address to the stack again. This is what the program is doing. Okay. So now, after this instruction, we have a ESP points to the return address, but this return address is not pushed by whatever function called the main function. The main function is called by a C library function called libc star or something, libc main to call your main function. Your main function is what you develop as a C developer. The libc star function is part of the C library calls the main function. So everything here is pushed by the libc library, but this one is pushed by the beginning of this code, your main function. So then everything after that is similar to a regular function. We have a push EBP, move ESP to EBP. So if we keep doing this, this is what we get. Then here we have another push ESP. Sorry, ECX here. And the ECX was pointing to here, and we push it, the value of ECX to the stack. So we have a saved ECX, and this is a pointer, it points to here. The reason we want to do this obviously is our code will use ECX. So we want to save ECX. So this is what the stack looks like after this. We have return address, 2 copies of it. Well, obviously they have the same value, 2 copies. We'll have save the EBP, save the ECX. To hack this one, we need to check the epilogue of the program to say which return address is actually used, or are maybe they are compared. We don't know because there are 2 copies. Right? We need to overwrite the correct copy. There are 2 copies. Maybe this one is used, the original one is used, maybe the new one is used. We need to check that. We also need to decide where to put the arguments. So let's take a look at the other code. So here we have the call to, this is probably the call to string copy. And before string copy, we push EAX to stack. So we know the address of the buffer, which is EBP minus 10. Note that it's EBP minus 10. So EBP was here, okay? So 10 is 16 bytes, which means from the beginning of the buffer to the saved EBP is 16 bytes. And we already know we have 4 bytes used for saved ECX. So the buffer here is actually, we have 12 bytes. Remember at the C code level, it's 8 bytes, but here we can say we actually have 12 bytes there. So after this, we now we are at the end of the program. We're going to clean up and return. So here what we have is we have a move EBP minus 4 to ECX. So this is to restore the same ECX, right? Because EBP is 0, right? Not safely. EBP is here. EBP minus 4, save the ECX. We move that to ECX. We're trying to restore ECX. After that, we do leave. Leave is move and pop. So after that, we have ESP points to this return address, ECX here, and we save ECX here. Then we have one more step, load effective address ECX minus 4 to move this one to ESP. So after this one, ECX minus 4. After this instruction, ESP will point to the original return address, and the ESP where the ECX will point to AXIC. Then we will do return. So what matters is where ESP points to, because return will use whatever ESP points to. So you can see that there are 2 copies of return address on the stack, but the copy created inside main is never used. When we return, we're still using the original copy in this case. So if you want to exploit this one, you still need to override this return address. However, the strange thing is the saved ECX. The saved ECX determine where is that, because the saved ECX is here, points to here. And this one determine where is the return address. Because you have that instruction ECX -4 move to the ESP. So if the ECX is has some garbage value, it will change your ESP to some garbage value, and then it will cause you not to find where is the return. Then you may get some garbage for your return address. So one way to solve this is you'll exploit somehow maintain the value of ECX. Before you exploit or after you exploit, the ECX 4 bytes should be the same value, should stay intact here. Okay, that's one way to solve this one. So the exploit can look like this. So this is stack, and this is your exploit. We have 12 bytes of buffer. Doesn't really matter what 12 bytes it is. Then we have the saved ECX. Once you get this value, you can debug this to get the correct ECX value. However, there's another problem is last week I didn't give you a tool which will make the stack have the same address with or without GDB. Because some of you already noticed that if you debug a program or do not debug program, the GDB will be different, right? Because the stack will be different. That's because GDB, when you debug something, the GDB will push a lot of information out the stack for you to use, for the program to use. That's why when you debug a program, the stack will always have lower address than without using GDB. So actually today I'm going to show you a tool to the tool will calculate how much bytes automatically to make them have the same address. Anyone solve this one? Okay, so you guys use another approach? Yeah, another approach. So it's not. Okay. We use this one. Huh? This one? This one? Okay, is it? What this one is used? Okay. Yeah. Yeah. So you can say that there are many different ways you can try to exploit this. But let's go back to this way. So in this approach, you can keep this one intact. So when we restore ESP, ECX will point to here, and this part you overwrite, and those are the arguments you want to use. So this is definitely exploitable. Several ways to exploit this. Any questions here? So I see probably 5 people solve this one. Okay. Good. Yeah. My exploit. Yeah. Okay. My exploit uses this approach. Yeah. Oh, yes. Well, I did it last year, so all the code I developed last year from scratch. Last night I was trying to, so before every class I would go over those again to make sure they still work. Okay, so the 64-bit version, the trick is because the address there are several zeros, so you need to return to the middle of the print secret function to do that. Because the beginning there is a zero, so you cannot really, if you input 0 there, you cannot overwrite that. So that's the key for the 64-bit version. Okay, so going back to what we're going to learn today. So last week we started doing the sequential buffer overflow to overflow the return address, but we just overflow the return address to some existing code address, function address. Now we know how to return to any function we want, even functions with parameters. So today will be our first class to do return to share code. So also we will say your first share code. We will dissect a share code to see how it works. So this is obviously your control flow hijacking attack. Okay, so we have yeah. Wednesday I have an office hour, so you guys can join, so we can debug them together. So you can show you guys. Okay. So this is a vulnerable program we're going to exploit. Very simple program. Main function calls a vulnerable function. The vulnerable function has a global variable, local variable buffer, 30 bytes here. Then we have gets. Gets is also a vulnerable function because it can take arbitrary long input, and gets do not take input from the command line arguments. Instead, it takes input from std. So then it just returns. So for this one, it's better for us to disable address space layout randomization and do that using this command here. So we already know how to override the return address. We just need to inject enough data. We also know what we want to override, which is function address. But what if we do not want to? There is no function we want to call in this case. We want to take full control of this computer with this vulnerable program. We want to get a shell that takes any command. So what can we do? Then we can use something called Shear Code. So the buffer looks like this. The stack looks like this. We have the buffer. We have the saved EBP. We have the return address. This is the function frame of Overflow. If we overwrite this, we can overwrite from here to go up many bytes actually. Thousands of bytes, even more we can do that without directly crashing overwriting. So the return address here, we can control what is the return address we want. And so far, we're not really utilizing these parts, right? All we have been writing to these parts are just garbage. We don't really care that. So we can actually utilize that by adding some code here. So this is called code injection attack. So instead of writing garbage here, we put some code, obviously binary, machine code. We call it share code. Then the return, we're not going to return to a function anywhere. We return directly here. So what will happen? Then it will keep executing our share code. So our share code will give us a shell. So a problem here is we need to know, let's say this is our share code. Our share code is 20 bytes, and you have to execute at the very first byte of that share code. If you don't do that, you run into some invalid instructions, eventually trigger a second fault. So we need to know the very accurate address of the beginning of share code. Sometimes it's hard to get. So far in our examples, we debug everything, we get everything but sometimes it's hard. For example, even if I set up there is a tool to make sure the address you got with and without GDB are the same. However, if you attack a remote machine, obviously you cannot use your tool on that machine to run GDB, which makes sense. So another trick we can use is we put a knob. This is called a knob set in the beginning, in the front of the share code. The share code is what exactly gave you the share. The knob set is just instructions, doesn't do anything. For example, there is a 1 byte knob instruction for the 90. So this is a binary code. That's 90. It's machine code. So this instruction doesn't do anything. Just give the EIP to the next byte. That's it. Of course, there are a lot of other instructions. They could be equivalent to this. Don't do anything. So if you put a big knob set in front of the share code, what you can do, you don't have to jump to this exact location. You can jump to the middle of this, right? To make things even. Oh, there's another thing we'll talk about later. Okay, so now let's see how we can hack this program to give us a shell. So this is disassembly of Overflow. We have the beginning is push EBP, move ESP to EBP, the subtract 38. I'm not sure how big that is. That's 38. 56 bytes, subtract the 56 bytes from ESP, then subtract again, then the EBP minus 30 is actually where the buffer is because it gets with the buffer. So the buffer is EBP minus 30, 30 in hex, so that's 48 bytes. So in C code, it's 30 bytes, 30. But in binary, you can say it's actually 48 bytes. Then we call get. So to hack this one, we are going to use some share code. So in today's class, we're now going to learn how to write share code. We're going to just use this piece of share code. In the second half of this class, we're going to do CTF challenge. That challenge was not developed by me. It's on a server, so that's why I asked you to bring a computer. You're going to SSH into that server, then try to use this piece of share code to get a share from that server. So then there are a lot of websites. So this is a website, ShareForm. They host a lot of share code for different architectures. And this is a 28 bytes share code. I think I've seen something for 32-bit version, maybe 23 bytes share code. Yeah. So this one is 28 bytes. Actually, we don't need those. Oh yeah, we can say later. Even this one, we can change it to 23 bytes. So this is a piece of share code, and this is what it looks like. Okay. If you look at the binary, this is what it looks like. When you look at this, you have no idea what this is. But this is share code. If you were to disassemble this is what we get. Okay. Those are the instructions. So we're trying to understand this share code 9 by 9, instruction 9 by 9. First of all, let me remind you that in x86, if you want to make system calls, this is how you are going to make system calls. You make a system call number, you put that into EAX. The name doesn't matter. Machine doesn't care about your name. The source is how this is where it is implemented. Then the first argument for that system call is placed in EBX, then ECX, EDX. Different system calls obviously they have different numbers of arguments. So for system call exit, the EAX is 1. There is only one integer as an input. So there is a fork. So what we are going to use is EXE system call. So this is a system call to create a new process. So this is what, it's not really create a new process, it's replacing the current process with a new binary image. Okay, fork will create a new process by clone the current process. So that's why there's a fork system call here. And strange enough that the 32, this is a 32-bit version of system call numbers for needles. Obviously, if you are talking about different operating systems, they have different system call names and numbers. Even how they place, where do they place the argument could be a little bit different. But this is how 32-bit Linux does it. Strange enough that the system call numbers for 64-bit and the 32-bit, they are not consistent. The 32-bit actually is number one, but 64-bit it could be 30 something. I don't remember, but they're not the same. So if you do a 64-bit version, you need to remember that they are not the same. Okay. So if you want to know the arguments for any system call, you can just in any terminal, you can type man means menu, man2, and the system call main. It will give you something like that. The 2 here means this is system call. I can quickly show you that. For example, if we do man2 exe7e, then we get the system call and we will get the prototype. We get the prototype of this. Here is function level, but eventually it's a system call. So you can see the first argument is the path name. The second argument is the command line argument you want to give to the program. Then you can also give environment variables, but we don't really need that for today's class. So the first one is the path name. We need to say which program you want to execute. We need to give the path. So if you do man2 open, you can also get the open or open at other system calls, the prototype. For some functions, there is not only system call version, but also C library version. Open has one. No, open doesn't have one. So open only has 2. Okay. So the manual section 2 is for system calls. Section 3 is for system libraries, C functions. For example, we can do man printf. Everyone uses printf, right? Oh, so this one printf here is what? That's because this is a command. There's a command called printf as well. So if we do 3, so this is printf3, which is a C function. Printf1 is a command. So command is number 1, system call number 2, C function number 3. Now going back to this system call exe7e, if we want to get us a shell, what we need is we need to run the shell program, and we're going to use this shell program being sh. This is also symbolically to point to a real shell. Then the first argument should be the name of this, the address of this string. Okay, this is the name of the shell we want to get, and this is C code, so this is actually the address of that. Then the second one is all the arguments. For this program doesn't really matter. We can give for all the C programs. The argv0 should be the name of the program. Argv1 is the first command line argument you want to give. So if we want to follow that, convention, here we should give the address of sh as well. But if you get 0, it still works actually. It still works. You don't we can still create a new process. Then the environment variable, we don't want to change, so just give 0. So That's what we want to include there. Okay, so let's look at the share code to say how it sets this up. The first instruction is exclusive or exe and exe. Okay, exe is the same thing with exclusive or to it. Obviously, we generate 0. So basically, the first instruction, the purpose is to move 0 to ex. Okay. However, we're not explicitly doing move. We're doing this. This will generate 2 bytes machine code, 3 0 and 3 0. Okay. The benefit of this is you can see there's no 0. There's no 0 in this instruction, and only 2 bytes. Okay. If we want to do the same thing with another instruction, let's say, let me find x86 assembly. Let's see. Oh yeah, here's the tool. So if we do XOX, so this one use Intel syntax. Intel syntax will just do this. Okay. If we do XOR EX, we get the instruction 2 bytes. We just solve that. What if we do the instead of doing this, we do a move EX 0. This is a Intel syntax. So the first one is actually the destination. Okay, we have we'll move the initial value 0 to EX. Then we assemble this. You can get the instruction E8, then 4 zeros. That's the instruction get. And the problem with this is there will be 4 zeros. And if the program, volatile program uses string copy, it will stop at 0. So you cannot copy all the share code. And also this is longer, this is 5 bytes. That's why the first instruction here, we have this. Now we have a 0 in EX. The next instruction, we push EX. So basically we put this 0 to on the stack, which is EX is 4 bytes. So I draw the stack here like this. I always draw stack high at the top, low at the bottom, and also left hand side is lower address, right hand side is higher address. So we push 4 bytes here. Then we push those 2 strings values there. Looks like quite random, but they're not. We're pushing them there. But let's try to understand their location first. So this is the value, and the 4F, 2F is least significant byte. Then another 2F, 7368. 68 is a higher address, right? So which means back here, 68 should be here because the right hand side is higher address. Then 73 is here, 2F, 2F. Then we push again this value. So now the stack is like this. After this, oops. After this, we move. Okay, I don't have one. Oh, I do have an animation for that. Okay, so now let's try to understand what we have there. We put. So now we put 12 bytes. So if we start with what if this is a string? Then we start with the low address. The lowest address is here. Then we go up to here. It's here, right? So this is this is low address. We go up here, here. So what if this is a string? Then what would be that string? So if we transfer it here to the string, then we look at the ASCII table. The string actually is a slash bin slash sh. That is what we're pushing it. We're actually push the string. those two weird lines, we are pushing a string onto the stack. Okay. You may ask why there are two stashes. Does anyone know that? Why there are two stashes? Stash. Okay. Actually, for Linux, it doesn't matter how much stashes you have. They will be used as one slash. Let's say, let's do ls bin. You can get everything. If I do ls, anyone tried this before? I have so many slashes. So Linux will consider that as one slash. Yeah. So let's do zip. There's no zip. My keyboard is not working. That's weird. So no matter where you put the slash, they will be the same. It will be the same. So they will be considered as one slash. So that's a feature of so that's how Linux interprets this. Because of that, it doesn't really matter how many slashes we put here. But the reason we put two slashes is obviously for padding. So we use the slash for padding in this case. Then after this one, we have move ESP to EEX. So because there are two pushes, after the second push, ESP points to here. Now we move ESP to EBX, so EBX points to it. So EBX points to the string, right? So EBX has the address of that string. And remember in system call, EBX is the first argument. Yeah, question? Yeah. Well, let's say in that case, if you only use one slash, then you have to put a 0 at the end of this, right? Yeah. And then you cannot put a 0 there because exactly that will make it a 0 somewhere here, right? And obviously we push this one. Obviously this number is in this instruction. If you have a 0 there, then that number will be here, right? So you cannot copy everything. It will be terminated. That's a reason. Okay, so now we have EBP points to the string, and the EBP is for that EXE EBP is the first argument. Then we have move EAX to ECX, and ECX is the second argument. Like I said, we just want to set it as 0, and we already have EAX as 0, so we move EAX to ECX. After that, obviously, EBX is the environment variable. We also want to set it as 0, so we're going to move EAX to EBX again. So after that, we set up all the registers we need. Oh, not yet, not of the EAX. EBX we set up points to the string, ECX 0, EBX 0. So next we need to set up EAX, which is a system call number. In this case, it's number 11, which is B in hex. So we move B to AL. Obviously, we can also do B to EAX instead of AL. AL is but this will be shorter and this will not generate zero. Then after that, we just make the system call, which is the int instruction. And in Linux, the system call is always int 80. That is the system call instruction. Why is 80? That's because how Linux is designed. From Intel's, the CPU designer's point of view, it has an interrupt table. And that interrupt table has many entries. And some of the entries for hardware interrupts, some of the entries for exceptions, and some of the entries for system calls. Actually, one entry for system call, and that's specifically for system call. So when you execute this, you will go to Linux kernel to handle system calls. I remember in Windows it was 21, I think, but in 21 in hex. In Linux 32-bit version, I'm not sure about 64-bit version anymore. Okay, so if everything is successful after this instruction, we should be able to create a new process, right? But you see there are 3 more instructions. Why do we need that? Technically, it's over after this. If this is successful, we will be executing the share program. But what if it is not successful? If it's not successful, it will keep executing, right? If this means it's not successful, it will keep executing. So if we do not have this, then we don't know what garbage we have after our share code, and that will trigger segment fault. Okay, so if you are a attacker, that will expose that you are attacking this machine. Well, for no reason, your computer is crashing. That's why there are 3 more instructions here, and those are simple ones. The first, we make EAX 0 again. Then we increase EAX. So EAX now has value 1. What is value 1? Exit. The system call exit. Then we just call int 80 to trigger this one. Okay. Now this program will explicitly call the system for exit to exit, so it will not crash. It will not generate any segment fault. So that is the reason of those 3 instructions, 5 bytes. So technically, the whole share code here will have 28 bytes, but if it's successful, we'll only need 23 bytes. It can be even smaller. Okay, now let's overwrite this program. Which one we're doing? We're doing return 4. Okay, let me see if we're doing this after return. Oh yeah, we can take 5 minutes break first. Then when we come back, we're going to hack over return 4. Okay. Before we hack that program, I forgot to show you how the cracking for is the version different. So as you can see that all of them generate from the same source code, and I use a flag load stack projector there, so we will not have any stack cookies. We haven't talked about stack cookies yet. We're talking about it next week or the one after that. So cracking 4, which is easy version for this flag. The correctly for H hard version, I do not have this flag. So this one is the default one. So you can see the default one I'm not using preferred stack boundary. Okay. So if I do not give it that option, what will happen is GCC will actually use 16 bytes as a boundary. GCC will align your main function stack 16 bytes. The reason GCC does that is actually because Intel has some special instructions for SSE2 instructions. SSE2 instructions. Those instructions are for kind of like for vector computing. So it's like single instruction, you can handle multiple down. So it's best of all vector down, matrix, those kind of things. So GPU will use something like this, similar idea. Okay. So a limitation of those instructions at a hardware level, circuit level, is they require the stack to be aligned in 16 bytes. And that's why by default, when GCC generates the code, you will align your stack at 16 bytes. But obviously, our main function, vol foo function, doesn't use any of those SSE instructions. That's why we can safely give it boundary 2 or 3. 2 means 2 power 2, which means 4. 3 means 2 power 3, which is 8 bytes. So, so this one is 16 bytes. That's the difference of crack V4 there. Okay, going back to our hacking here. So now we just need to figure out, we have the share code. We know we're going to put the share code in that buffer, but we do not know the runtime address of that buffer, right? So we need to figure out the runtime address of the buffer. To do that, one way is to debug the program, get the exact location, or in reality, if you have some other's computer, a more realistic approach is to just guess, to keep trying, okay? Because it's not like always you can debug on their machine, right? And also there are other protections anyway. Okay, so first we are going to disable address space layout randomization. Then we are going to use a tool. I didn't develop this tool, I just get it from GitHub. We are going to, the purpose of this tool is to make sure with or without GDB, your target program will have the same stack offset. So this is how we're going to use this tool. We use the name doesn't really matter. R$sh, then we can GDB the program arguments, then we can run you can debug this program, or you can directly run this program. You have to use the same tool with and without to have the same stack offset. Okay, so the first time we'll do this, we're going to put that 28 bytes of share code at the beginning of the buffer. Then we know the whole thing is 48 bytes, right? So there will be 20 bytes, we don't really care, garbage. Then save the EBP, we don't care. The return address we will get here. So we need to debug to get that. So first, let's debug this. We use r.sh gdb or. We will keep revisiting this program. This is a first program we inject the Shear Code. You can see I have so many versions of it: 64-byte version, 64-byte no stack execution, 64-byte no stack array. We will keep revisiting this this program later in this class. That's why I have so many different programs here. So let's see, where do we start? We debug this. We want to get the address of, so do we have the source code? Yeah, this is the source code. So the vulnerability is in val foo. So we can set a breakpoint at val foo, be val foo, then we just run this. Oh, by the way, when I use a tool, you notice that when I use a tool, all my GDB plugins are not working anymore. I didn't fix it. Okay. If you are interested, you can try to fix that. It doesn't really bother me that much. So if we just run this program, now we hit the breakpoint. So if we disassemble here, we're in val foo. You can see this is a get function, which will override the stack. We want to know the address of the buffer. So after this instruction, then we can get the address, which is the EBP minus 30, right? So if we set a breakpoint at this, B star this, then we do say continue. Now we hit this breakpoint, and at this point we know the address of buffer, so we can get the address of buffer. We can print EBP minus 30. Okay, so now we get the address of the buffer, which is let's write it down. Okay, it's FCA F8. Let me just put it down somewhere. Okay, so this is our buffer's address, right? So what we can do is, okay, the buffer's address is here. So this is where we are going to return to. So this return address, we are going to put that value. Then 28 bytes, the Shear Code, 20 bytes garbage, 4 bytes garbage. That's all we want. Let's see if we can make this work. I'm going to copy one of those here. Let's see which one's here. Oops, does it work? No. Where is that? Oh, this one. Okay, now it works. Okay, let's say in the middle, the 31 to 80, that's our Shear Code. 28 bytes. So we're going to construct a share code, 28 bytes. After that, we have garbage. So we can use A. How many bytes of garbage? 24 bytes of garbage, right? Because we're doing this one. Here is 20 bytes. Here is 4 bytes. So 24 bytes of garbage. We just put 24 A's there. Then we have the return address, which we just write down as say a F8. Okay, so that is our exploit. In the middle of the exploit, 28 bytes of share code. Then let's just redirect this to a local file so we can reuse it. Okay. Now we're going to debug that program again to see if it works. GDB or 4. Now we're going to break Wolf again. Then we're going to run this with that share code. We run it this way. We just run, and the share code will be redirect there. Okay, now we're running the program. Let's see where we are. We're at the beginning, so we just want to get to the end of the return. So when we return, we are supposed to return the share code. Let's see if it works. We keep going. We're F1. Well, we want to get to 20C. Okay, keyword 20C. Okay. Now we are at the return. Now let's try to return it. Let's do SI. Okay. Now we return to the stack. FF say 8 FF. Okay. So now let's say if that is our share code. If you do disassemble, it doesn't work because the disassemble command only works for functions. If you do that, you say this doesn't look like a function, it cannot be. But you can still do an exam. You can do exam, and let's do 20 instructions. So exam, then there is a slash, then how many data you want to exam. Then you can set the data as for example, X means you want to examine this as data. I means you want to examine this as instruction. So here we want to do I. Then we're already at the beginning, so we just put EIP here. So this is what we're going to do. Okay. So we take that's our share code, right? So we're at the beginning. We haven't executed anything yet. This is under our share code. Everything after that we didn't do it. No, everything after that will be the garbage, the A, right? Yeah, those are the A's. So the A's, when you interpret those instructions, actually increase its X, uppercase A. Okay. So now we just execute this step by step. We're supposed to at the address CB0D. We're not supposed to return. We're supposed to have a new process. Let's say CB0D. Okay. See? When we execute something, now we have a new. Now we're actually creating a new process. That's the share, okay? And the GDB is containing the breakpoint. The breakpoints doesn't work anymore because we cannot find function involved with it. Okay, so it means this actually works for when we do the GDB. So let's do this without GDB. So when we do this one, we need to do a cat here actually. We need to do this one. I think we should do this. Okay. First of all, we have to do the r.sh. So it will be the same address. Then we just type everything there. Also the account. Otherwise, you will not really take input. Even though you create the process, but the share process, you will not take input from you, so you need to put account here. Let's see if it works. Oh, looks like it works. It's thinking. Let's see. Who am I? It works. That's a shell. We got a shell. That's a shell we got because we have this share code. Okay. So in this example, we used the exact location, right? F8. Obviously, if there's one byte off, it will not work. Let's say F7, it will not work. Oops, sorry. Should be F7. It will not work. There's a second fault. Doesn't give us a share. If it's F9, another byte off, also get a segment fault. Doesn't give us a share. So we need to know the exact location of that. So to make this a little bit more flexible for us, instead of a waste that 20 bytes as garbage, we're going to put this share code here, and that 20 bytes here, and that 20 bytes we will just give it a lock. Show you what it looks like something like this, and we will use the same. We just use a simple lock like the 90. Okay, so we can just change this exploit a little bit. So at the beginning, let's do 20 bytes of lock, which is 90. 20 bytes of lock. Then here we don't need the 24. We only need 4. So we put this back to 8. So now we run this. We jump to the very beginning of the lock, right? So yeah, it works. Or right now we don't have to jump to the very beginning. We can jump to anywhere in the lock. So we just do a FF. This will be the beginning of the lock. So this one, we're not jumping to here. We're jumping to here instead, or it's still lock. So we'll keep running until it use the share. Yeah. We don't have enough space. Oh yeah, we can, right? Yeah, we can. 24 bytes, then another. So we override this one. Yeah, because we don't need this. So we can do that. We can try that after this one. So we do this. Obviously, it also works. Right. So you want to try 24 bytes of log. 24 bytes. Then we don't need the A anymore. So we still jump to FF in the middle. That work. What's the problem here? 24. Are we using EBP anyhow? No, we're not using EBP. So it should work. 4 bytes. But we're not using EBP. So it doesn't really matter. The EBP. You're ready 24 bytes and then you get 20 bytes. Yeah. Interesting. We can debug this to see what's going on. I don't think EBP is a problem there. 24 bytes, 28 bytes. Yeah. That's a good point. Oh yeah, so gets may put 0A there, right? A new line there. That may be the problem. Yes, so maybe we cannot do 24 bytes. We can do 23 bytes. Let's try 23. Yeah, that's a good point. Let's see if 23 works. Nope, 23 also doesn't work. Oh, 23. Oh, if we do 23, we need one more byte here, right? So we need 8 here. That's weird. No, that's not the reason. Okay, let's debug. This is fun. I like this because I didn't prepare for this, so let's figure out what's going on. So, okay, this is F8 is correct, right? Now we do GDB for with Overflow. We run with Shear Code 32. Symbol here. We keep running until we return, I guess. So that leave should not cause any problem. Oh, let's see, after FA, so now we already after FA, so now we can examine the buffer a little bit. So exam, let's examine 40 bytes, 56 bytes, maybe 56 bytes from EBP minus 38. Okay, that looked weird. That's like our Shear Code. Oh, we haven't coded that. Oh, okay. Sorry for that. Let's see. Oh, yeah. 2 more steps. Okay. Now, okay. So now this is our Shear Code. We have the walks. Then there's A. Oh, this is a high, so this is actually the end event. This part is our. So where is our? Not very clear. So EBP. Let's just do EBP 12 bytes. So EBP should point to our saved EBP. Then it has our return address. Okay, so return address is correct. This is correct. So this one we didn't touch. No, this one, what is this address? This is should be part of the Shear Code, right? 41, 40, CB 40. That should be the last 4 bytes of our Shear Code. Let's see if that's one. Yeah, of course. Because we're not using the EBP. So before we were just putting values there anyway, right? Okay. So C0, 40, CD8. Something is, looks like there's 1 byte off. There's a 41. We don't have a 41 here. What is 41? 40 is 41A. Okay, so we are okay. So, but this one, which is highest? This is C0. 0 is highest. So it's C0 40. Okay, okay, looks correct. Okay. Looks correct here. Let's see why now we add move the B, leave is correct, nothing wrong. And we jump to our Shear Code. Okay, looks like everything's working so far. Let's put that here as EMP. Okay, looks like everything's working. So we begin with our missing engine. So this is where we are supposed to create a new process. Okay, looks like everything's working. Let's keep running. We're looking at the address say B24. Say B24. Running. Didn't clear the process. That's weird. Oh, here's a problem. That's not an int. That's a DOS. I think it would be a DOS. How do we get a DOS there instead of the int? Where do we start? Should we run it again? Okay, this one here looks good. I need to set some a little bit more. Here looks good. We still have a. Let's go to say B0F, starting from there to say if the instruction is correct. Say B0F. Okay, from here, instructions. Do this one. Well, in 11, so this one 12, 17, 1, see. Yeah, there was the push and the problem. After the push, this one changed. I don't know if it's the right one. What is this? Yes. So how many bytes is this? So somehow after that, it's not int anymore. That's a problem. Okay, we can take this offline. I probably we can use a better tool because here we don't know if the value is really changed. The value should not change actually, but I'm not sure after the push something changed. Then when we interpret this, it's not an int anymore. Okay, we can bring this offline. I will get back to you tonight to see what's going on. This is fun. We'll figure it out. Okay, so we already tried that with slab here. We have a 20 byte slab. Obviously, 20 byte slab sometimes. By the way, those are the commands you can use when you do this test. 20 byte slab is not big enough. How can we have a much bigger slab? We want to have a much bigger slab, bigger than 20 bytes. We want to have a slab with 1,000 bytes. How do we get it? here we have a small slab, right? So the reason we have a slab is to increase the chance that we hit in the slab. So we not need to know the exact location, eventually transfer the control to share code. But if the slab is big, very big, then we don't need to know the exact location. We just simply guess. Eventually we can hit the slab, right? Then how can we have a huge slab there? Because here we don't have enough space. Right? Yeah, where is it? Just look at the picture, where is it? No, we do not want to go that far. Just look at here. Where do we go? Yeah. So actually, what we can do is we can put on top of this, right? So those 48 bytes, we're not going to use it. Actually, 52 bytes, we're not going to use it. We go to the return. So after return, we have a huge step. Then after the huge step, we have the share code. So in that case, the chance we hit that will be much higher. Something like this. Here, 48 bytes of garbage, another 4 bytes of garbage. Then we just do a huge step. Then let's try this one. So this time, since we're trying, we're not going to use that. We're not going to debug. We're not going to use the tool r.sh to give us the same offset. We just try this. First is 52 bytes of garbage, then return address, and the return address, we don't know the exact value, so we're going to try later. There's a format here. Okay. This is a return address. Then this is our share code. So here we can add a huge log. By huge, we can do like this. Okay, I have a huge knob here. Then we just go to here. And so I'm not using that stack tool. RSH. Then let's just run this to see if it works. Ooh, we got lucky. It works. Nope. No, it's not working. Let's see. What's the problem? There's a broken pipe. Am I missing a quote somewhere? Okay, the quote looks fine. Okay. Let's see if this one's correct. Okay, let's try it actually. Syntax is correct. And why there's a broken pipe? Okay, that broken pipe could be overflow here. So now we get just to change our address. Let's say this is the address we get with GDB. So we're going to change something higher. Right? So we can change something big. So A, we just change to C. It works. Oh, it works. Just because like I said, the GDB will push a lot of things there. So that address is what we get when we have GDB. So without GDB, the address will be higher, and we'll have a huge slider there, so we just change this to say something. And luckily with keeps there. We can even make the slab even bigger. This address, maybe this one we want to change to D. Let's try. No, too big. Say F. Yeah, say F works. So we have, in this case, we have a 4 megabytes slab. Almost the 4 megabytes. So that is the 32-bit version of this. Let's keep working on. I think I will slide for the 64-bit version. I have all the commands here in the slides. So when you do your homework, you can try those. Something important is the cat here is important. Without the cat, you will be able to get the share, but you're not inputting anything to the share. Okay, so that's important. Okay, so the same code, let's do 64-bit. The only difference is, so everything, the overwriting is actually the same. The difference is the share code. So this is a 64-bit version of the share code from assembly code. So you can see here in 64-bit, you can directly reference RIP in your instructions. That you cannot do that in 32-bit version. So 32-bit version, you cannot directly access EIP. On the 64, you can directly access RIP. So what we do is, this is a inherent syntax assembly. We'll move 59 to RX, 159, because, like I said, the system call number will be different. We search Linux system call table. So, okay, this one has some 64-bit version. We are looking for EXE right? You can say 64-bit, the system call number is 51. No, they don't have 32-bit, whatever. 32-bit is 11, so they have different number there. So RAX, we put 59 there. Then we know the string address. And it's very convenient. We can just do RIP process to get the string address to RDI, then SIDX, we will use 0. Then instead of int 80, we use another instruction for system call. This is an instruction. This is a new instruction for system call in 64-bit. I think we can use this instruction in 32-bit as well. Yeah. But the older version, very old CPU, we don't have this instruction. New, we have this instruction. Then we can, so this is a assembly, the share code. What we can do is, let me show you. I have this make file here. This is a share code. The assembly is here. This is what I just showed you. Then we compile or assemble this assembly. We make share code. Then what we get is we call those two instructions. We first use we still use GCC to assemble or compile assembly code. First of all, we do not want C library functions, so we give flag low STD library. And we don't want dynamic link, so it's static. So after this, we get this L file. So you can see this L file is a 64-bit elf statically linked. That's it. Then, since this is an elf file, it has a lot of meta information. It has all the headers, right? We don't need those. We only need the instructions. That's why we use the other being utility tool for OBJ copy. You are already familiar with OBJ dump at this point. So OBJ copy is to copy elf sections out. Then you can just want to dump the text section, and what we get is the output will be share code rule. So that we're only share code rule will only have the instructions. So if we do a file on this, it will not be able to tell what this is. Okay. So if we do XXD on this, so if we do XXD, those are the instructions. Okay, you can see the string. So using the same approach, we can hack the 64-bit version. Let's try 64-bit version. So this time let's have a huge select. So we're not going to debug this. We just try. Or 64. 64. The variable function. So it's still 48 bytes. So we can do, let me see something I can copy from there. So we have the share code. How many bytes? How many bytes are share code? Probably have that in my slides. Oh, 7 bytes. I'll just do an XXD there. Okay. So this is 32. Then this is 44 bytes. There are a lot of zeros in this. We're using gaps. 44 bytes. 12, 32, 40, 44 bytes. Oh, this is weird. There are a lot of zeros. Okay. I don't remember this one. Let's try. 44 bytes. So the first category will have 44 bytes. Then we need 44 bytes, another 4 bytes there. Then we have the saved RVP 8 bytes, so it's 12 bytes. Then we have the return address. So we should be 12. Is that right? 12. Okay, everyone is still following. 44 bytes. Okay, let's revisit this one later. Okay, everyone is a little bit tired of this. Okay, let's do something fun instead. Now I want you to hack by yourself. Okay. So we're going to play an online war game called how do I pronounce this? No. The behemoth. Okay, behemoth. Okay, Code over the while, they have all kinds of challenges, starting from very simple ones, critical ones, and also binary hacking. So you can. So this is a website. You don't really have to visit this website, but you need to use SSH tool to log into this place. I'm going to copy this line to our Slack channel and also copy the share code for our Slack channel. Then you can log in, look around first to see what you can get and what you can hack. Here, this is a credentials. I'm going to give you the 32-bit version of the share code. Okay, I will just copy the whole thing to you. I don't know what version they have on the server for Python. So okay, over there. So the one in the middle is the share code. Okay. So how do I send this to you? We don't want to type this. This is like 28. Yeah, you already typing? Okay. find the binary you want to hack. It's somewhere in the file system. There is only one binary you can hack at each level. This is how the game is designed. You hack one binary, you go to the next level. There are several binaries, but only one of those you can access. Yeah, there's only one of them you can access because only one belongs to you. Well, there is one without requiring the beginner squad, right? That one belongs to you, so you should be able to run that. It looks like we have too many people accessing the server at the same time. Oh my gosh. This web, I never realized this website is poorly designed. We only have 4 people here. And we're performing with also technology. Let's see what we can do. Okay, what do you guys want to do? Do you just want to use this as homework? Then you can go home now. Okay, so we use this as a homework. Yeah, so I will give you guys this one as a homework. Okay, next time I will not use this website. Never realize. I will never like this big spot. Okay, this is actually all I have for today. Class is over. Next week we're talking about injecting the share code in other places and talk about how to defeat this kind of attack. So this will be our first time talking about defense. Cool. See you guys next week. Yes. What if the workspace?